Stephen Hawking's A Brief History of Time is a landmark work that delves into the complexities of the universe, unraveling profound scientific theories and ideas in an accessible way for general readers. Published in 1988, the book addresses fundamental questions about the origin, structure, and future of the cosmos while integrating the history and progress of science in exploring these mysteries. It examines the roles of relativity, quantum mechanics, and cosmology in shaping our understanding of reality, blending scientific rigor with philosophical reflections on existence. Hawking begins by recounting the historical evolution of cosmological thought, from ancient Greek philosophers like Aristotle, who argued for a geocentric universe, to Ptolemy, who refined this model. This sets the stage for the Copernican revolution, where Nicolaus Copernicus posited a heliocentric system, fundamentally altering humanity's view of the cosmos. Galileo and Kepler further advanced this paradigm with empirical evidence and mathematical precision, laying the groundwork for Isaac Newton's laws of motion and universal gravitation, which unified celestial and terrestrial mechanics. Newton's deterministic model suggested a static, infinite universe governed by predictable laws. However, this concept was later challenged by the discovery that the universe is dynamic and expanding. This idea was first proposed by Edwin Hubble, whose observations of distant galaxies revealed a redshift in their light, indicating their movement away from us. Hubble's findings became the cornerstone of modern cosmology, suggesting that the universe had a beginning, an idea encapsulated in the Big Bang theory. Hawking explains the Big Bang as a singularity, a point where all known physical laws break down due to infinite density and gravity. This led scientists to question what existed before the Big Bang and whether the universe had a definitive origin. The interplay of time and space, as described by Albert Einstein's general theory of relativity, became critical in understanding these concepts. Relativity showed that space and time are interconnected in a four-dimensional continuum and that massive objects warp this fabric, creating what we perceive as gravity. Quantum mechanics, another pillar of modern physics, introduced a probabilistic framework to the behavior of particles at the smallest scales. Hawking discusses how these principles clash with the determinism of relativity, particularly in extreme environments like black holes, where both theories must be reconciled. He explores the concept of quantum fluctuations and their role in the creation of matter and energy, offering insights into the origins of structure in the universe. The book delves deeply into the nature of black holes, objects with such intense gravitational pull that nothing, not even light, can escape. Hawking explains their formation, from the collapse of massive stars, and describes their defining features, such as the event horizon and singularity. He introduces the groundbreaking idea of Hawking radiation, which suggests that black holes can emit particles and eventually evaporate, challenging the notion that they are entirely black and eternal. Hawking expands on the concept of the arrow of time, differentiating between three types: thermodynamic, psychological, and cosmological. He connects these arrows to the second law of thermodynamics, which states that entropy, or disorder, always increases. This irreversibility of time gives a direction to the universe's evolution, from a highly ordered state at the Big Bang to increasing chaos. Cosmic inflation, a rapid expansion that occurred fractions of a second after the Big Bang, is explored as a mechanism for explaining the universe's uniformity and large-scale structure. Hawking discusses how tiny quantum fluctuations during this period were amplified to create galaxies, stars, and other cosmic structures we observe today. Hawking considers the role of unifying theories, particularly the quest for a theory of everything that could reconcile quantum mechanics and general relativity. He explains how such a theory would provide a complete understanding of the fundamental forces in particles, from the behavior of subatomic particles to the dynamics of galaxies. While acknowledging that string theory and other frameworks offer promising directions, he concedes that a definitive theory of everything remains elusive. The nature of time is a recurring theme throughout the book. Hawking examines whether time is finite or infinite and whether it has a beginning or end. He introduces the concept of imaginary time, a mathematical construct that provides an alternative way of describing the universe, bypassing the singularities that arise in real time. Hawking also reflects on the anthropic principle, which posits that the universe's laws and constants are fine-tuned for the existence of life. He considers the implications of this idea, debating whether it suggests design or is a consequence of a multiverse, where countless universes exist with varying properties. The book concludes with philosophical musings on the nature of existence and humanity's place in the universe. Hawking questions whether the universe requires a creator or if it can be explained entirely through scientific principles. He leaves this question open, acknowledging that science and philosophy may ultimately converge in addressing it. In A Brief History of Time, Stephen Hawking masterfully bridges the gap between cutting-edge scientific theories and the curious layperson, unraveling the mysteries of the universe in a manner that is both profound and comprehensible. The book serves as a testament to human ingenuity and our relentless quest to understand the cosmos. By blending history, science, and philosophy, Hawking invites readers to ponder the origins and fate of the universe and humanity's role within it. Ultimately, the book inspires a sense of awe and curiosity, urging us to continue exploring the profound questions that define our existence.